today's video, we will talk about tilted plane machining using G68.2 in Fanuc or Cycle 800 in Siemens. In 3+2 axis machining, the rotary axes are used only to orient the part, after which all cutting motion is performed using pure 3-axis interpolation. This approach combines the simplicity and stability of 3-axis machining with the accessibility of 5-axis machines, making it ideal for features such as angled holes, pockets, slots, and planar surfaces. Functions such as G68.2 Fanuc 3D coordinate rotation and Cycle 800 tilted working plane enable this by mathematically rotating the work coordinate system to match the desired machining angle. Once the tilted plane is activated, the programmer can continue to use standard XYZ movements, while the control automatically transforms them into the required rotary axis positions A, B, C. The tool remains fixed in orientation during cutting, ensuring rigid machining, predictable cutting forces, and excellent surface finish. Key advantages of 3+2 over simultaneous 5-axis machining. Now the question is, why learn G68.2 or Cycle 800 when CAM already generates it? Although CAM software can automatically output G68.2 or Cycle 800 for 3+2 operations, a professional CNC programmer must understand the logic behind these commands, not just run post-process code. Post-processor validation and debugging. In 3+2 machining, even a small error in plane definition can cause incorrect feature orientation, axis over travel or limit alarms, machining on the wrong face. Understanding the tilted plane parameters allows the programmer to verify correct or simplified CAM output directly at the machine. Safe throughout and first article runs. CAM systems often generate multiple rotary moves and safety retracts. With G68.2 or Cycle 800 knowledge, programmers can log the rotary axis once orientation is achieved, convert complex CAM output into clean, readable 3-axis code. Now let us look at shop floor adjustments without reposting. Inspection feedback often demands minor angular corrections. Then fixture or setup deviations. Instead of reposting from CAM, an experienced programmer can adjust the tilted plane definition directly, saving time and maintaining control. Now, what is a key takeaway for 3+2 machining? CAM may generate the code, but understanding G68.2 or Cycle 800 gives the programmer authority over orientation, safety, and accuracy. This knowledge is what separates a CAM-dependent operator from a true multi-axis CNC programmer. Now let us understand the details. Happy learning. Let us understand how Euler angles are defined. Now by definition, Z-axis is shown as a blue axis and X-axis is shown as a red one and Y-axis is shown as a green one. Now, by definition, Euler angle controls the tilting by first about z-axis and then about x-axis. So whatever tilting you need to orient the z-axis to the tool axis, you need to have multiples of rotations x. So the first one is z about z, second one is about x, third one is again on z. So depending on the requirement, you need to adjust which one to rotate, how to rotate. This is the original condition of the rotary axis. That means C0 and A0. Now look at the coordinate system. Z-axis is pointing towards spindle and the x-axis is pointing towards right. Now assume that the C-axis is indexed by 90 degree. So what will happen is your coordinate system will automatically rotate by 90 degree. So then the x-axis will be pointing down or towards the operator. Assume that it is C 180 degree, then x-axis will be towards left, and C 270 x-axis will be up away from the operator, or instead of 270 you can also consider it as minus 90. Now assume that it is indexed A minus 90. So A axis is indexed and the C axis is in the original condition. So you can see that Z is pointing towards the operator, X axis is to the left, to the right, and Y axis pointing up. Now for doing anything on this side, the requirement is that the Z axis should be pointing towards the spindle. That means like this. Now remember the Euler angles, definition of Euler angles. So the first rotation should be on Z axis, then it should be on X, third should be again on Z. Now the requirement is to make Z axis in line with the spindle axis. So just one rotation is enough, that is on X axis. So the first rotation on Z is 0 and the second rotation is 90 degree, that is in the minus direction, and third rotation is not required, so third rotation is also 0. So I0, J minus 90, K0. So this is the first angle. Then imagine that the C axis is rotated by 90 degree. So the original coordinate system will rotate with the part like this. So the X which was in the right direction will be now to the bottom side. Now again, to make the machining onto this, what is required again, you need to have the Z axis to this, aligning with the spindle axis. So a rotation like this can help, but then Euler angle do not allow you to rotate about the Y axis. So what is required is, first you need to make X parallel to the operator so that the next rotation can be on X axis. So the first rotation is on Z axis, that is plus 90 degree. Second is on X axis, that is minus 90 degree. So it will be I 90, J minus 90. Third rotation is not required, K 0. First, we will see the G68.2 on a table configuration with A and C axis with A minus 90, C0 position. So this is how the table will look like after tilting. This is the machine coordinate system. This is the work coordinate system original after tilting. And this is the ideal coordinate system to be working on in tilted plane. So the expected result after G68.2 is this. So this is the operator view. Without tilting, the table will look like this. The x-axis will be parallel to the operator. So this is same as in line with the machine coordinate system. And the z-axis will be always pointed towards the spindle. But you can see this original coordinate system after tilting, the z-axis is becoming like this. So now using G68.2, we need to make this z-axis in line with the spindle. So this is the expected outcome. That means tilted coordinate system. So if you look at the Euler angle definition, the first rotation is about z-axis. Now in this case, you do not need any rotation about z-axis because straight away if you rotate this coordinate system about x-axis, you will get this. So the first rotation on z-axis, that means about z-axis, is 0 and the result is I will be 0. And then next you have to make z-axis perpendicular to your current coordinate system. That means z-axis in line with the spindle. So if you tilt this coordinate system in 90-degree about x-axis, you will get this result. So when you are looking from the positive side of the axis on which it is getting rotated, if it is the coordinate system is getting rotated in the clockwise direction, it will be minus, and in the counterclockwise direction, it will be positive. So in this case, it is clockwise, so minus. So you get J minus 90. And with this, you are getting what you really need to make z-axis in line with the spindle and x-axis parallel to the operator. So already what you need is already there. So no need of one more rotation. So there is the other rotation about z-axis is not required. So the command for G68.2 would be G68.2 I0, this is the I0, J minus 90, J minus 90 and K0, this. So this is how we decide how IJK values need to be defined for G68.2. Now let us see a new position with A minus 90, C 90. So what happens is A is already indexed to 90 degree, and then C is also indexed. So the the x-axis which was parallel to the operator now has become 90 degree index. The result is now x-axis is pointing downwards. So this is the original one. So now what you need to do is, for bringing the coordinate system like this, first you need to rotate the x-axis by 90 degrees so that it becomes parallel to this, and then about x-axis you can index so that you get the final result. So here there is a 90 degree indexing about z-axis. So why is it plus 90? Because this coordinate system is getting rotated in the counterclockwise direction. So you get I90. And then next, about x-axis, you are again indexing so that your z-axis become parallel to the spindle axis. So here j minus 90. Why j minus 90? Because when you look from here, this is on the clockwise direction. So that is why it is j minus 90. And then next, no further rotation required, because here itself we are already getting the required coordinate system. So the result of G68.2 is I90 j minus 90 K0. Now let us see the third position, A minus 90 C180. So here you can see the original coordinate system which is having the x-axis towards right. Now it is towards left because now the c-axis is indexed by 180 degree. So now you can see that this is the original coordinate system after indexing. Now to bring this z-axis parallel to the spindle axis, even without rotating on the first one, we can get it because x-axis is already parallel. So if you simply rotate on this 90 degree, the z-axis can become parallel to the spindle axis. But we are not doing that because we want the x to be towards the right side. Then only the usual coordinate system will work here. So the first action what we are going to take in the first step, looking at Euler angle, the first rotation is about z. So this is z. So you are rotating it by 180 degree. So you are rotating it in the clockwise direction. So we are considering it as plus 180. So in this case, the rotation can be in either way. You will get the same 180 degree. So you rotate this way or this way, you get the same result. And then next, after the x-axis is oriented to right by 180 degree indexing on the coordinate system, then you rotate the coordinate system by 90 degree so that z-axis become parallel to the spindle axis. So that's it. Third indexing is not required. So finally you will get I180 j minus 90 K0. So I180 is this, j minus 90 and then K0. Now look at the last one, A minus 90 C270 position. So C270 position can also be called as C minus 90 because it is rotating in the other direction. So you can see this x-axis is now pointed upwards in the tilted condition. Now what we can do is the first rotation can be on z-axis. So the first requirement is to make x-axis parallel. So if you simply index it by 90 degree, and it is minus 90 because when viewing like this, it is getting rotated in the clockwise direction. So I minus 90. Then after that, you can index further by 90 degree so that your z-axis become parallel to the spindle axis. So J minus 90. Next, third step is not required because already you achieved what you wanted. So the final result is G68.2, I minus 90, J minus 90, K0. I minus 90, J minus 90, K0. Now let us look at tool center point compensation. So keeping the center point in the same condition, that's how TCPM works, tool center point management. So if you want the center to remain in the same place and then the pivot point to move away, then there will be a compensation in X. It will look like this, and there will be another compensation in Z axis. It will look like this. Now we will see how is the calculation done. So you can see that now the head is tilted by certain angle. So this is the pivot length, that is from the pivot point to the spindle face, and this is the tool length. So if we take out this portion and then try to make a geometry out of it, so this length we have already discussed here. One is pivot length and another one is tool length. So if we add both, you get L2. So you know that this is also L2 because same thing, and this will form a radius of this, keeping this pivot point. And let us consider that the angle made by this indexing is angle theta. So this is the compensation in Z, which is equal to B here, and this is the compensation in X, which is equal to A here. So if you calculate A and B, you can get the compensation in X and Z. So if you consider this as a right angle triangle with 90 degree here and angle theta defining this angle, so your cos theta is adjacent side by hypotenuse. Adjacent side is this L2 minus B. So this distance is L2 minus B, and this is L2. So cos theta equals L2 minus B by L2. So from that you can derive B equal to L2 minus L2 multiplied by cos theta. That means L2 into 1 minus cos theta. And then sin theta is opposite side by hypotenuse. Opposite side is A and hypotenuse is L2. So A by L2, from which you get A equals L2 multiplied by sin theta. So this is how the machine will calculate. We need not know how it is being calculated, but this is how it is done in the background. This knowledge will help you to troubleshoot if at all any error is coming. And the correct tool length is very important. Correct tool length and correct pivot length. Pivot length is usually a one-time activity, and in regular intervals, say for example 6 months or 1 year, you may have to verify that and calibrate it. And then tool length is based on the tool what you are mounting here. So unless your tool length is correct, this compensation will not be correct. So here what we need to note is this pivot length is specific to the machine. So even if the brand and the model is same, one machine to other machine, because of the manufacturing variations, you will get some variation between the pivot length of one machine and the other machine, even if most of the spec remains same. So what happens is, if you imagine that you do not have G68.2 or Cycle 800, then you need to make program for each and every machine, taking the actual pivot length and tool length. So that is how this function is helping you. You develop the program for one machine, and the other machine, the same program will automatically run, taking the actual pivot length into consideration. That will happen in the background. Now let us see an example for G68.2, which is usually done in Fanuc. So this is the 0 point, original 0 point for the part. So it is shown like this. So operator is standing here. This is X plus, Y plus, and Z plus. Now for easily doing this, what we can do is we can shift this 0 from the original position to the new position. This is before rotation, and the value is 25. Then we can rotate it using the G68.2 definition. So how we are doing this? First we are indexing the A axis and then C axis, say A minus 15, C0. So this 15 degree is what this part demand. So first we just index the table, and then we call G68.2. This X, Y, Z represent the new coordinate system before rotation, and IJK is what we have just seen now. So each angles considering the Euler angles, and then G53.1 for orienting the tool axis, and then you can call to the center of this hole by commanding G0, X40, Y30. Why? Because by doing G68.2, Y25, the origin is already shifted here. Then when you are tilting by 15 degree, so this origin remain the same, and then you can call the tool to center of this hole by defining X40 and Y30. Then we will call a drilling cycle G81 Z minus 10 R2. Then we cancel the cycle and cancel the plane rotation G68.2. So G69 will cancel the G68.2. Now let us see how the same thing is used in Cycle 800. So Cycle 800 in Siemens is having a interface like this. So you can define some name for the tilting and whether it is a new one or you want to make it additive with respect to another coordinate system. So it is to avoid confusion, it is always better to define a new one. And then this is the reference point before rotation. So if we need to make any change, so we wanted to shift the 0 from here to here, so 25 mm in y axis. So before rotation, this XYZ is what we need to do. X is 0, Y is 25 and Z is 0. And then this is the rotation. So the rotation is about X axis 15 degree. And when you look at X axis, so the rotation is onto the clockwise. The table is getting rotated in the clockwise direction, not the axis. Table is getting rotated. So it is considered as plus. And now after tilting, the 0 becomes here because we have defined it that way. Now if you want to move the center from this corner point to center of this board, that is what is ideal in this case. So the 0 after rotation, after rotating, we will move x by 40 and y minus y by 30. Why? Because after tilting, the x0, y0 position is offsetted to the center, so that the further calculation will be easier. So this is the new 0 point before rotation and this is the new 0 point after rotation. Now assume that we are working on a machine with a B axis. B axis means the rotation of the rotary tilting is about the y axis. That is what is B axis. Now the other rotary axis is C axis, which is about Z axis. So this is the 0 0 condition. That means B0 C0 condition. Now look at the coordinate system. So always the Z axis will be pointing towards the spindle and the X axis is to the right of the operator. Now if you are doing the indexing of the C axis, then the C axis will come here, C90 will come here. So when it is getting rotated, the original coordinate system will get rotated like this. Now imagine that you are tilting the B axis. So this is B90. So this is B90 C0. So you can see that the X axis is pointing up, Z axis to the left and Y axis away from the operator. Now imagine that you want to do something on this face. So the requirement is Z axis should be pointing towards this. So you know that you cannot, Euler angle do not allow you to rotate about y axis. You can rotate only on x axis. So what you can do is first you can make x axis parallel to this so that next rotation can be like this. So now this is the original condition. The first rotation is on Z axis, that is minus 90 degree. Next rotation is on X axis, that is again minus 90 degree. Now you can see that your X axis is pointing towards the operator. whereas x-axis should be pointing towards right. So the third rotation should be like this, again on z-axis. So this will be a plus 90. So that means K 90 degree. So again repeat. So this is the original condition. Original condition is like this. So the first rotation what we are doing is like this. So that is I minus 90. Then next is J minus 90. Then K 90. So then your Z axis will be pointing towards the spindle and the X axis will be pointing towards right. Then you can, as usual, whatever you are doing in 3 axis, similar fashion, you can continue.